Okay, hello everyone, and welcome to the AI Club. My name is Uddesh Soman. I am currently a student at Ujjain Engineering College in 7th SEM for Bachelor's in Electrical Engineering. And today we are going to look at one of our advanced classes in NLP course, Transformer and BERT. So I'll give a slight introduction to what is a transformer, and then we'll move straight to one of the pre-processed models that involves transformer, that is BERT. So starting with a brief introduction to transformer. So transformer model is something that can achieve state-of-the-art results. And honestly, since its introduction, uh, it has overthrown more or less the recurrent neural networks and convolutional neural networks, both in terms of BLEU score. This is bilingual evaluation under study score and training time. So we'll get to that in some time. And one more thing, one more concept about the transformer that makes them interesting and computationally efficient is that long distance context around the world. So far, what we have seen about the models, they either take word to vector or trace dependencies like in spacey models. Well, the transformer models are actually capable of getting longer distance context from entire paragraphs, from long sequence of sentences. They can find all those they can find all the context. They can find all the relations. That is one advantage with transformer, and it was developed by Vaswani in 2017. It is basically a type of neural network architecture. So those who are familiar with the concepts of deep learning, they will know what a neural network is. Transformer is a kind of neural network. If you see the architecture of a transformer, it resembles more or less a neural network, and we'll be using neural network libraries available in Python like TensorFlow, Keras to actually implement the transformer. And initially, it was developed for NLP tasks like question answering, text prediction, sentiment analysis. But it has also found application in image recognition as well. So this was just a brief introduction of transformers. We'll move to BERT. So right now we have here the archer of a transformer. So these are this basic architecture of transformer model is it shows a multi-head self-attention mechanism. So if you see here, there are multiple attention mechanisms. So what is that? It will find relation context with words. So these are all mechanisms for that. Feed forward networks, addition and normalization layers, and you can see connections. It's fairly complicated architecture, and we won't be go to the detail of the architecture. This one here is just for your reference. If you want to go into details, if you want to study the architecture in details, I'd recommend you to check the reference provided here when you get the PPT. So, so this is basic introduction to transformer. What is transformer? And so I'll get to BERT. Well, before that, I'll just want to say that what a transformer actually is. Transformer is a way to convert data in a specific form and then make predictions. So just keep that statement in mind. Transformer is a general method of transforming data in some form and then make predictions. So now we'll get into the working of BERT. Before getting into working, let me tell you what is BERT. So BERT was created and published by Jacob Devlin in 2018, and it originated from Google. And since 2019, Google has been using BERT in its search engine for natural language sync. It's pre-trained model. It's pre-trained on an absurd amount of data. And obviously, if you check the papers and the documentations of BERT, you'll find that there are multiple versions of BERT. The original one actually comes into two sizes, BERT base and BERT large. So BERT base is actually trained on some 800 million words from book corpus, and BERT large is trained on English Wikipedia. So that amounts for around 2.5 billion words. That you can just assume how big the amount of data BERT has been pre-trained on, and that is the reason BERT has such excellent performance as compared to other neural networks for NLP related tasks. Let me know why BERT. Since we have so far we have seen spacey models, we have seen the use of that LSTM for predicting POS tags and all that. We can by now we can just imagine how we can create a NLP pipeline using Keras, using already available neural networks. Then why use BERT? Why is the need for a BERT? So the need is mostly what the advantages of BERT, and it is that it is pre-trained on a great amount of data. So while applying on a small data set that you have, you do not need to train it. You can just take BERT as it is and make predictions, even if required. You can make some amount of fine tuning instead of training the whole network. You can do some fine tuning, fine tune couple of layers, and you will get excellent results. So, how to do that? How that fine tuning and use of BERT is done? I'll cover that in the practical session. Here, I'm just going with the basic theory of BERT. Okay. Next, about contextual embeddings. So, if you remember, word to vector and token embeddings that were earlier done in spacey models and our neural network that we created using bidirectional LSTM, there were no contextual embeddings. However, in BERT, we have contextual embeddings. The any embedding that is done on any token, that is done with reference to a whole context by considering the whole paragraph or the whole corpus. This contextual embedding is done. Actually, I'll cover this one how it is done in our today's session. And just to summarize what makes BERT so great. So first of all, it's trained on a lot of data. It's a pre-trained model trained on a lot of data, so you can just simply assume that it will give great performance. And even if required, we can fine tune the layers. It accounts for words context. So while using BERT, you can be rest assured that whatever word that you are processing, its context is taken into account, and it is open source, so free to use. You can just download the library, download the pre-trained models, and use them as it is. So this was general introduction to transformers, BERT, why we prefer BERT. If anyone wants to discuss anything, anyone has any confusion, I'll be happy to sort out. Otherwise, will we move forward? Anyone?
No, maybe in the next session, maybe it will be more clear. Right now, it is, yeah. Okay.
Um, if you have confusion with any part, please let me know. I'll explain it again. Hello?
Actually, from this, it is not clear. So,
Which part?
this bird, no, means it is just some 3, 4 lines are there and not able to make any thing out of it.
Uh, okay, then I'll explain how BERT works. I think
Mhm.
that will make it more clear.
Yeah, yeah,
I'll move on to that now.
yeah.
So, working BERT. So, working of BERT is a simple order of business. That is, you have to fulfill the task of fill in the blank. You have a statement, you have a sentence, and you fill in the blank by removing some word and making prediction for that word. So here we have the woman went to the store and bought a blank of shoes. So general assumption could be a pair of shoes. Well, the task of BERT is to train itself to predict that word, pair of shoes. Okay. And the key thing about BERT is this bidirectionally trained. So during the process of training, if you remember bidirectional LSTM, there were actually two layers. One which takes the sequence from left to right, another one which takes the sequence from right to left. BERT actually does both these steps simultaneously, from left to right and right to left. Both happen simultaneously to process the sequences, word sequences, and that makes the sense in order to make the sense and to get into deeper sense of language context and to understand the flow and the performance obviously better than single directional language models.
Soman, just a second. So
Yeah.
here to Dr. Shailesh, I want to make a couple of things clear because he expressed the doubt that things are not clear. So I will tell that BERT is just a model similar to word to vec. Like word to vec CBOW, you remember, like continuous bag of words. So in that we have context, and in that context we predict the middle word, right? So we have a context, and we predict the middle word, and in that process we get the word embedding, a word to vec embedding of that particular word. Okay, so that is the with a shallow neural network we do that, and we get word to vec embeddings. So similarly, BERT is also another mechanism of getting your context-based embeddings of the words. Like embedding means to get simple words. To embedding means to convert word into numeric vectors. So those word to numeric vectors is your embeddings. So context-based embeddings we get context-based embeddings using BERT, and BERT is another mechanism of getting word to vec is one mechanism, and BERT is another mechanism of getting word embeddings. And so we discussed that why it should be used, because it is based on transformer models. So very long context, like if suppose you are using a word and after 50 your 50th word is there in the sentence or in a paragraph, and that particular 50th sentence, 50th word is having context or some relation with the second word of the paragraph. So that kind of long relationships, or even 150 words or even 200 word kind of long relationships can be maintained using BERT. And as BERT is trained on a very large corpus of very large corpus of English language corpus, so you can expect very nice accuracy with the help of BERTs as compared to word to vec and globe. So BERT is giving better results, and it is based on transformer model. So how it is based on transformer model and what the transformer model is, we are not getting into that detail because it is a separate topic. And for that, understanding transformer model, if you are interested in, I think we have already provided some links wherein you can go through it and you can understand what is transformer model and how BERT relates to transformer model. So those resources we are providing, and if you are interested, you can go through it. But in this class, we are much it's applied class, and we are much more interested in how to use BERT and how to use get better result using BERTs. So that's what is our main aim in this class. So that's why we are not going into details of transformer model and all those things. So with this background, do you have any question? I think any question, Dr. Shailesh?
It is clear now.
Yeah, so it is just another scheme of converting word into vectors, just like we had word to vec. So this is a transformer-based scheme of transformer-based scheme to convert words into vector, and it is context-based, and it can relate to very long context, very long context, and it is trained on a very large corpus. So these word vectors are more giving give more accurate result than what you get with the help of word2vec and globe. So that's what is the background.
Okay.
Yeah. Okay. So let us proceed, Soman.
Sure. So, as I was saying, the basic task of the BERT would be to predict the missing word from the sentence or corpus, or predict words in general. How it does that and what is the training process, I'll discuss in the later slides. Just for now, keep this in mind that this is our basic task to fill in the blank. Next point, that it is a bidirectionally trained. So the bidirectional training would actually mean any input that we provide is simultaneously evaluated from left to right and right, the whole sequence. And that bidirectional evaluation or bidirectional training actually helps us get a deeper sense of language context. So as sir said that you have a 50 word long paragraph, and the last word actually relates to second or third word of your paragraph. So that kind of large range of context or deeper sense of language context, that can be achieved using BERT, which is difficult or almost impossible with single directional language models. So I'll move on to working. So before we go into all those processes, training process, we need some pre-processing. So pre-processing will have only 3 steps in pre-processing. And that pre-processing is actually extracting some metadata out of sentences. Metadata is additional information that comes with any input or any object. Metadata is like, if you remember when we download videos, there is bunch of metadata like frame rate or aspect ratio or the size, pixel size of your image, pixel size of your video. So kind of here we have to generate some metadata. So here the pre-processing is basically these 3 steps, that is generating the metadata out of our sentence, out of our input sentences. So first is token embedding. So whenever we create a sentence, if you remember in Spacey, tokens were created. So similarly here, tokens are created. Each and every word in your input text is converted to tokens, assigned a token, and additionally 2 more tokens are added in your sentence, that is CLS token, which is added to the first sentence at the beginning of your text. At the beginning of your text, uh, at the beginning of your text, only first sentence, this CLS token is added, and another SCP token. This token is added for separation at sentences. So in case you have multiple sentences, this SCP token will come into play. I'll show you one example after this. Segment embedding. So segment embedding is done for each and every sentence. So each sentence is considered a separate segment and provided a token in metadata, like a marker. For sentence A, sentence B. So each and every word in sentence A would carry this tag A. Each and every word in sentence B would carry this tag B, and so on. Next up is positional embedding. So positional embedding is just its position of each and every word in an array. So here are the 3 processes. So consider the sentence, our input, my dog is cute, he likes to play. Now each and every word becomes a token. So if you see here in token embedding, each and every word becomes a token, and there we have the CLS token at the beginning of our text, the in the beginning of sentence, the CLS token, and the sep token at the separation of sentences. Next, segment embedding. As I've said, the segment embedding is for classifying tokens belonging to particular sentences. So each token belonging to the first sentence gets the segment embedding A, if you see here. Next, each and every token belonging to sentence B gets B. And if we have more sentences, that process goes on with more segments. Position embedding. So the position embedding is just position, including this CLS and SEP token. So positional embedding of each and every word and these tokens as well. So starts from 0 and up till the end of our text. So this is a basic pre-processing is done, or addition of metadata. In other words, addition of metadata in our to our text is done to actually this metadata is also evaluated to make predictions. Next up, the main step that we have to look is prediction. So one of the so there are actually two prediction processes in that happen inside BERT. First is masked LM. So each token, the single token prediction process is done using masked LM. So the idea is simple: randomly mask 15% of words in the input. So 15% of words randomly selected are actually replaced with this mask token, and the model then tries to predict them. But also one more approach is made uh, on those 15% mask tokens, is that only 80% tokens are actually replaced with mask token. The 80% of tokens are replaced with mask tokens. 10% of the tokens are replaced with random tokens. Random tokens means in order to create error sets, means in order to create error sets or to consider wrong predictions as well, random tokens are replaced 10% of times, and 10% tokens are left unchanged. Unchanged tokens. So they will the original token takes back the place. So this kind of process happens within BERT, and those mask tokens are then used for prediction. So if you see here, we have the sentence here: Harry Potter is a series of fantasy novel written by J.K. Rowling. Our sentence is broken down into tokens, and these tokens, the 15% tokens, are actually replaced with this mask token. During the training, BERT will try to predict these mask tokens and compare it to the actual text. It is a supervised training, so it will obviously have an actual text, and it will compare it with actual text, whether the prediction is correct or not, and hence shift the weights accordingly.
See, where I want to just comment here one small thing. See, Dr. Shailesh and others like Himanshu and everybody, when we did our predictions with the help of name entity recognition and POS like part of speech tagging, that's where what we needed, why we needed training data, how the training data was. So training data was plain English, and in that the NER like named entities were named with the hand tagging. So labels were done using hand tagging. Similarly, in POS training of POS tagging model, POS tag like verb, noun. So for each sentence, verb, noun, adjective, determiner. So those kind of things were tagged by hand for a big corpus. And then that data was used for training of that particular NER model or a POS tag model. But here, you need not do any, see, someone please correct me if I'm wrong. So here, one advantage, obvious advantage of this masking I see is that for BERT training, you need not do any hand tagging, because in the sentence itself, BERT automatically is masking some particular words and separating out it as labels. And then in training, during training process, it try to predict them. And once the predictions are done, it automatically compares with Harry, off, return, K. So whatever is masked, so they automatically done. So this tagging process, which was required manually, so here is no manual tagging is required. Am I correct in saying this, Soman?
Yes, sir. Exactly. That's what the transformer is doing.
Yeah. So here manual tagging is not required. Dr. Shailesh, is this understood?
Yes, yes.
Yeah, Himanshu, is it understood?
Yes, sir.
Yeah, so let us proceed.
Okay, thanks. And exactly that was one advantage of transformer, that you do not need to pre-process most of the training data. You can just have the entire text in the form of a paragraph or couple of sentences, and you can just pass it as it is to the transformer, even for training as well as for prediction purpose. There is no need of pre-processing. The pre-processing layer is already embedded within the the transformer, and the transformer will do the embedding, uh, that
Yeah,
pre-processing embedding
so
that we have seen earlier, and make these predictions for the tokens
by
for training.
sorry for interrupting, someone. So
Yeah,
by pre-processing here, we mean that to prepare the training data, you need not do any labeling with your hands. Manual labeling is not required for any train data. So that is
yeah,
all automatically done by the model itself.
yeah, exactly. Thank you, sir. So moving forward, once this mass token prediction is one of the processes, another process that takes place within BERT is next sentence prediction. So consider here we have sentence. The man went to some store and he bought a gallon of milk. So you can see these two sentences relate to each other, right? The man went to some store and he bought a gallon of milk. So is the second sentence follows the first sentence? Does the second sentence follows the first sentence? Is there any relationship between these two sentences? So there is a label is next. So whether a given sentence uh, is the next sentence to the uh, uh, previous sentence, that is actually done by BERT. So we can it's clear from the name next sentence prediction that is done, and once next sentence prediction is done, it compares it with the original document whether the prediction is right or not. So here you can see the man some mass token to the store. Penguin are flightless birds. So you see there is no relation between these two sentences. So not next, which means this is not the next sentence to previous sentence. So that is next sentence prediction technique. Next sentence prediction actually helps us with that longer context. So not just context between words, but context between separate sentences as well. Relations to explore the relationships between sentences. That can be done using BERT, and that is one of the process that inherently happens inside BERT. The transformer does that, and the next sentence prediction for the training process, as far as the training process is concerned, the half of the times the second sentence comes after the next one, which means half of the times it creates a data set with the sentences such that the first sentence is actually related to the following sentence, and half of the time they are randomly selected sentences, randomly selected sentences that hold no meaning to them, hold no meaning previous sentence. So if you see here, we have two such examples. So I completed high school, and then I joined undergrad. So yeah, this makes sense, right? You complete high school, then you join an undergrad course. So is that correct order? Yes. Then it will create a training scenario where then I joined undergrad, I completed high school. So that is not correct order, no. It the relationship between these two sentences isn't clear. It's if you see if you'll check in a corpus, if you check this in a document, you'll find that this would be incorrect. So is that correct order? No. And that kind of data is used for training for the next sentence prediction process. So this kind of pairs of sentence become input while training each sen- each sentence followed by either a sentence that follows it, or a completely random sentence, and again in swapped order. So one following other, or other following the first. That kind of swap order as well. The basic task at this
Yes,
point
Soman,
is,
sorry for interrupting, Soman. I think you can read out these two lines which are there in the
Yeah.
below this example on the right hand side. That will make more sense.
yeah, of course. So that I was actually explaining these lines, but yeah. So during the training, model gets as input pair of sentences. So as I told, since you need to take one sentence and predict whether the other sentence follows the first sentence or not, or the next sentence to the first sentence or not. So for that, it will get a pair of sentences. That pair of sentences can be in the swapped order as shown here, or this format as well. That second sentence comes after the first one, or it is a random sentence taken from the full corpus. And what our model has to do, it has during the training, it will learn to predict if the second sentence is the next sentence in original text as well. Okay, it will make prediction of this label, that next label, that whether the whether the second sentence is next sentence to the first sentence or not. That is the basic basic task of next sentence prediction, and this is the process, how the training data is, how it is trained within the BERT transformer. So is that clear?
Yes, yes. I think it is clear. Yeah.
Okay.
Uh,
So
can you show that previous slide, just previous to this one?
yeah, this one.
Yeah, this one.
Okay, so what's your doubt?
Yeah, okay. Now you can go.
Huh?
Now you can move on.
Okay, you just want to check that, right?
Yeah.
Okay, nothing. The meaning is here is just you have one sentence followed by another sentence, and if you have to predict that the second sentence, the second part of input, whether it is next sentence to the first or not. So if you see here, the man went to store and he bought a gallon, some mass token and milk. So you can see, yeah, this sentence is obviously related to the first sentence. You can say that this sentence is related to the next sentence. It will make prediction and check in the original text, the original training document or corpus that we have provided. It will check in it whether the is next label predicted makes is correct or not. Okay. That is the case. If it is not, then we have the label not next.
So is it required that first sentence should, while doing the prediction, first sentence should 100% match, or how much is the degree of matching should?
Sir, that is actually done with vector embedding and all that binary prediction process. And I'll there means this is all internal. So actually,
Okay.
even I'm not completely sure about that. But
Yeah.
as far
Like
as I have
this is
seen in
making
the
sure that the next sentence is in context or out of context. Like the first one is actually in in high correlation to the next one, and the second one is not that much.
Yeah, but according to, I mean, Shailesh sir's question, the extent that correctness I'm not sure about at this point. I'll obviously check it out and see if I can find something. As far as I'm concerned, as far as I have seen in while preparing the practical demo, I can say that mostly it takes the sigmoid function. So you will have some threshold that if it is 0 to 1, so if the relation that sigmoid function output is above 5, then it is next sentence. If it is less than 5, less than 0.5, then it is not the next sentence. So kind of like that.
Okay. Yeah, I think it's a fair assumption. Got it.
Yeah. So moving forward, yeah, training losses. So we have seen these two steps. Now obviously the training losses will correspond to these two steps. So the loss function will consider only the prediction of mass tokens and ignore the prediction of non-mass tokens. So this one is actually the training part and not for testing part. While training, BERT will consider any loss that occurs in predicting mass tokens. So while we are if you remember while creating those tokens, I said only 80% of the tokens will actually be replaced by the mass token. Here, only 80% of tokens are replaced by the mass tokens, 10% are replaced by random tokens, and 10% tokens are unchanged. And that is out of the 15% that we have selected for masking. So if you have like 100 words, then out of those 100 words, 15 words are selected. Of those 15 selected words, only 12 words are converted into mass tokens, and rest remain unchanged or replaced by random tokens. So the 8% means around 12 tokens of 100 around 12 tokens. Those are actually considered for that loss function. And just see here, most of these functions actually work with probabilities, right? There is some probability that whether it is right or wrong, and then you can just subtract it from 0 or 1, which means if it is predicted right, so how far it is from 1. How if it is predicted wrong, then how far it is from 0, that predicted probability. And whatever is that, you add up and calculate the log of that value. So that is log loss function. We have already seen. If anyone wants to revisit the log loss function, I would recommend checking our previous videos, or you can check online also for the log loss function. So that is one the BERT uses, and it uses it to calculate the loss of mass tokens. And as far as sentence prediction is concerned, then BERT required to predict whether second sentence is random or not, with the assumption that random sentence will be disconnected from the first sentence. So that is one basic assumption that is made while predicting the next sentence, that it is currently disconnected from the previous sentence, and after the prediction is done, it is checked in the original corpus. And the losses of these two processes are combined together, and in order to combine the losses, these two processes are done simultaneously. So if you see here, the model is trained with both mass DLM and next sentence prediction together, and this simultaneous training actually helps us to minimize the combined loss. Whatever be the combined loss of these two strategies, the training during the combined loss function is minimized, and that results in a good model. The only disadvantage here is that it is bit slower than unidirectional processes. So if you see the point number 2, this results in a model that converges much more slowly than left to right or right to left models, or in simply we can say the unidirectional models. So this is how training loss is computed for BERT, because right now we have seen there are two processes, that next sentence prediction and mass DLM. And for those two processes, you take both, the training is done simultaneously, and the loss is computed for both of them. So that was the general training process of BERT. If anyone has any confusion with the training process, you can ask it.
No, I think good.
Okay.
So we can go ahead.
Yeah. So coming to BERT use cases. So what are the cases or what are the scenarios in BERT is most widely used? Is first binary text classification. So if you see the process of masked LM, you can simply see that whole process is actually similar to binary text classification. Binary text classification is done using it can generate probabilities of each and every word, whether a word fits there or not, and it can reduce probabilities for that. Question answering task with paragraph. So please note that question answering task with paragraph. It needs to have a whole paragraph to make sense out of question and answer and bring answer to that question. That is one important point to note because I'll actually come up with that in next slide. Next, semantic similarity between pair of sentences. So whether two sentences are similar or not, we have seen similarity between words in one of our previous Spacey demos where we have seen the similarity of queen with various words. So that same process can be done with sentences if we use BERT. And the last is text summarization. So summarization is actually if you have a huge document, a whole big article or a research paper, you can create a short summary out of it using BERT. So since BERT is able to predict tokens, predict next sentences, do the question answering task. So a combination of these steps actually results in a text summarization engine as well. So that can be created using BERT. And the reason I emphasized on question answering task with paragraph is because the limitation of BERT is it cannot do the normal question answering task. So if you see the normal question answering task is like single statement questions, like the commands, the questions we ask to our AI models like Alexa, if we call what is the weather today, or what is if you ask the descriptive question like describe certain object to me. So that kind of situation is where BERT it these are the limitations of BERT. It needs a paragraph, reference paragraph to actually answer your question. It can do that with paragraph, but normal question answering task is cannot be performed using BERT. Text generator, so it cannot generate text out of the blue. If you just give a topic and expect it to give a whole article about it, that it cannot do. Machine translation is also one of the fields where BERT lacks. So why is that so? The reason for these limitations is that it's a bidirectional situation. We since it takes input from both directions. So since these cases, if you see here, the bidirectional input cannot be provided, or same input from reverse and forward context cannot be done for these scenarios. That's why BERT fails at these tasks, or these tasks cannot be performed using BERT.
One question on this.
Yeah.
This transformer, is it a separate entity, or is it a pre-processing tool of BERT?
No, sir. Transformer is a class. Transformers. What we are discussing is a transformer. BERT is a kind of transformer.
Oh, okay.
There are other models as well, and they come under the category of transformer. We are talking about BERT in this one. Certain more transformers are added as well. So if you want to check out how transformer works, we will not go into that in our session. Then that is beyond the scope of this session. So we'll not go into that. If you want, these references are provided here. You will get them with the PPT. You can check them out if you want to see how transformer works and the ideas behind transformer.
What I thought is the transformer and BERT are two separate entities, but now I think it's very clear thing.
No. BERT is a kind of transformer. So transformer-based models in NLP, that should actually answer your question.
Just a second. Sorry for interruption, Soman. See,
Yeah.
Dr. Shailesh, I think you are very much research oriented. So I would like sometime to you to, like, once you are familiar with how to solve the problems, hands-on being within BERTs and little bit familiarity of your familiarity with BERT increases, then we would like you to take a session for us on what is transformer model, how it works, and how BERT relates to transformer. So that's what we would like to hear from you once your familiarity increases with BERT in the somewhere sometime in the near future. Because your background is very much research oriented. So I think you will be the right person to explain us that what is a transformer model, how BERT is related with that, what are the pros and cons, and everything around transformer models you can research in detail and explain to this class.
Sure. Yeah.
Okay. And also to check out the transformer-based models that are transformer-based NLP models. So BERT is the one that we talked about. It was the focus of our class today. Another is GPT-3, so Generative Pre-trained Transformer 3. It's from OpenAI, and it's actually paid model. This one is not open source. T5 is open source model. T5 is one transformer model that is used for prediction. It's I'll show you the details. And Roberta, robustly optimized BERT pre-training approach. So this is BERT, but robustly optimized. There is some sort of hyperparameter tuning as well as more more training of the model. So if you want to check out more details, I'd recommend you to do some R&D about that. So these are the famous NLP famous transformer-based NLP model. And
so this GPT-3 is very interesting to know that it is from OpenAI, and OpenAI is Elon Musk promoted company. So they have developed a very nice, very highly trained model GPT-3, which they have trained on entire internet content. So it can do all the NLP related tasks, but it is a paid one. So, and it is promoted by Elon Musk company called OpenAI. But it is paid one.
Not so expensive though. It costs $18 for some, I think, a 1 month worth of use.
But is it unlimited usage or it is per transaction usage?
That I'm not sure. I saw the.
I think it is per transaction usage, Soman. $18 will anybody will buy and do unlimited usage, so they will not allow that. I think it is maybe most basic subscription is for $18, and as you cross a certain number of transaction threshold, you will be charged based on your number of transactions. So that's what my guess is regarding GPT-3.
I think I'd recommend just if someone wants to use it, then they should check the documentation.
Not we. We are happy with BERT. Yeah, we are happy with BERT.
We'll stick to BERT for now. Yeah. So how does NLP models leverage the transformer architecture? So transformer models have mostly replaced the NLP models such as RNNs in practice. And if you going into details of just fewer details of some of the models that I have shown, the GPT model is actually a decoder of transformer structure. So GPT, if you have seen in BERT, we had that encoder as well. GPT does not have encoder. It's simply a decoder, and it is unidirectional in nature. That is note. BERT is based on transformer encoder. It involves encoding of text and then making predictions, and it is bidirectional in nature. T5 is interesting. It is actually it involves both these processes, encoding as well as decoding, and decoder transformer structure. And it is very similar to the original transformer implementation or transformer implementation. So in order, if you want to know more about these things, I'd honestly recommend you to check out the documentations, check out the articles, because obviously it would be so too much to cover in a single session.
Yeah, so I think in the right hand side box, which is little bit shaded, I think these are the links to the original papers of GPT-3, T5, BERT and all. So these are original paper by which GPT-3, T5 and BERT were introduced. So you can, if you are interested in having a look at the original papers, you can have a look through these references.
Yeah. So finally, the last topic of our session, fine-tuning approaches. So if you, as I mentioned earlier, if needed, already these are pre-trained, already these transformers are pre-trained models. They are pre-trained on a huge amount of data, and then they can be directly used for prediction. But in case still, if you want a specific, if you want to tune them for a specific purpose, or fine-tune them for better results, then fine tuning can be done. And along with that, there are multiple approaches to fine tuning. Three of them are shown here. So training the entire model on label data, you can train the entire model, make everything trainable. Training only higher layers and freezing the lower layers. So lower layers are mostly the part of our neural network, that dense layers consisting of neurons. Or in case of transformer, there are this additional batch normalization kind of layers. You can freeze those layers and actually train the higher layers, that are encoders. Encoders are actually trained as well. So you can train the encoders, or freezing the entire model and training one or more additional layers added on top. So you can add more layers on top of your model and train those layers as well. Instead of training your model, you can take the model's output and train another layers. So these are fine-tuning approaches. Fine-tuning, I think it'd be better if you want to check out fine-tuning. I'd again recommend you to check one from our deep learning session. We have covered fine-tuning in that lecture, which in using of pre-trained models and transfer learning. We have covered fine-tuning in that. You can check out how fine-tuning is done for any neural network, and then same approach can be used for BERT as well. So that's why that's all for today. If you want to check out tutorials, coding demos on BERT, you want examples on BERT, so the links are provided in the slide. You can check them out using these links. Again, we will discuss one example as in one of our sessions as well, the practical session. So that's all for today. Thank you very much. If you have any questions, please, the floor is open.
Yeah, so before we start Q&A session, I want to add a couple of words. So I think BERT was introduced as late as 2018. So not even 3 years, 3.5 years. And even Google started using in 2019. Okay, so it is a very recent phenomena, and it's very, very involved and complex technology. So considering the student background of Uddesh Soman, I think he has done a wonderful job and given us a flawless presentation on BERT and made us understand. So thank you so much, first of all.